Okay, so we want to evaluate the integral by changing to cylindrical coordinates. We have the integral from 0 to 1 of the integral from 0 to square root of 1 minus y squared of the integral from 0 to the integral from x squared plus y squared to the square root of x squared plus y squared of 2yz dz dy dx. Well, okay, well, let's start with the integrand. I might need room for a picture over here, I don't know, so let me start over here. So triple integral. Good idea is to write down the correct volume element right away, so you get the right extra factor in there. So what's the correct volume element? You need an extra factor of, I might need some extra room too. So r dz dr d theta. Usually that you can pretty much count on the order being dz dr d theta. It doesn't have to be, it's just why not stick with one because one's not easier than the other. Not usually anyway. Okay, and then we might as well handle the integrand while we're here. What's y in cylindrical coordinates? Same as polar. Okay, I'm going to write the 2 out here, and then r sine theta. And then what's z? Trick question, it's z, right? In cylindrical, anyway. Okay, now this is where the stuff from the very first chapter, and it's, I don't know if you remember, but I warned you. These are the surfaces we learn calculus on. That's what I meant when I said you got to learn how to graph this stuff. So this bottom limit here, do you remember what that graphs to be? A parabola, right? A circular parabola, actually. So you think of it as z. This is the bottom limit on the z, right? So z equals x squared plus y squared. I think we could actually get away without graphing it here, but you should have in your mind a picture of what it looks like. So it looks like that satellite dish, kind of elongated satellite dish. None of them go this deep, right? But at least not proportionally. That's the best I can do today, apparently. And then, so that's kind of the floor, right? And then what's the ceiling gonna be? Okay, set z equal to this. It's a surface in space. What is it? No! It's a cone, top half of a cone, for crying out loud, right? And I'm just kidding. It's hard to know all this stuff, right? But you gotta get comfortable with it to be good at this stuff. Now, interestingly, the vertex of this cone is in the same spot as the vertex of the paraboloid, right? But it's kind of skinnier, at least for part of the way. And it'll look something like that on the inside. And you know, when they intersect, they're going to have the same curve of intersection. Up at a height of z equals 1, I suppose, right? So you can then think of the cone as the ceiling and the paraboloid as the floor. That's how it makes sense visually. Anyway, for this particular one, I think you can get away without drawing that picture because it's a direct transformation to cylindrical coordinates. What is x squared plus y squared in cylindrical? R squared, and then the square root of r squared would be the top, right? Which would just be r, the ceiling. Does that make sense? Okay. And then as far as the outer limits of integration go, well, it might not be the full circle of intersection as the boundary, right? But when you project down without the zeros there, if it went the full way, you'd get this circle of intersection, wouldn't you? Again, more stuff you don't necessarily need to get the right answer here, but it does help, I think. What does, okay, 0, I think it's clear what 0 is, but what does this guy describe? Okay, it's the limits on x, right? The middle limits of integration are the limits on x, so x goes from 0 to root 1 minus y squared, right? If you take this boundary equation, given by the upper limit on x, symbolically you can recognize that as part of a circle by just squaring both sides and putting it in standard form. If you square both sides, you get x squared equals 1 minus y squared and add y squared to both sides, you get x squared plus y squared equals 1, don't you? So so that's a circle of radius 1. But I don't think we're talking about the whole circle here, are we? So imagine projecting this guy down. You get the circle as the boundary, and the interior is a disk, right? But the outer limits of integration limit how much of the disk we're going to integrate over. And if you look at the original integrand, it's actually set up the outer differentials dx, dy, which corresponds to what kind of rectangles? Horizontal. But the horizontal rectangle only goes from 0, x equals 0, to the circle. So visually, going backwards, that's, if you were setting up the integral in the first place, that's what the picture would have looked like. So what part of the circle does x equal the square root of 1 minus y squared describe? Not the top part, not the bottom part. Well, really, if you're just talking x equals square root of 1 minus y squared, it's really the right-hand part of the circle, right? Now, we are going to be limiting it to the first quadrant because of something else. But just talking about that equation, x equals the square root of 1 minus y squared is the right half of the circle, right? However, knowing the outer limits, the original outer limits, y goes from 0 to 1. Oh, that's down here to here, right? So that does put you in the first quadrant, doesn't it? So it's the outer limits that give you that you're limited to the quarter disk, really, right? Okay, so now that we know what we're integrating over in a type of cylindrical, well, really it's polar, right, for the outer limits of integration. What does R range from? Think radially from the origin. Think draw on a spoke. What does R range from? 0 to 1. That's a circle of radius 1, right? Square root of 1 is 1. And then theta is going to range from, now here's where you have to be careful. You're tracing out just the part of the disk in the first quadrant, the quarter disk. So 0 to pi halves. Okay, let's clean this. I don't know if I'm going to evaluate this whole thing for you, but let me clean it up the way you should. Integral from 2, I brought the 2 outside, 2 times the integral from 0 to pi halves, integral 0 to 1, integral r squared to r, and then what do we have inside? R squared sine theta times z dz dr d theta.